Alright, hey y'all, welcome back. We just started our force unit, so I thought I'd go through and video talking about everything. I'm going to start this video with just talking about free body diagrams and also Newton's three laws of motion. But before I even start that, let's just go through our basic variables. We have time as seconds, position as meters, displacement is change in position, which is also meters. You have your velocity, which is meters per second, acceleration, meters per second square. We also have gravitational acceleration, which we also write as a little g, which is meters per second squared, and that's 9.81 if we're on Earth. And then our new unit is force, which is actually newtons. Newtons is the SI unit, but that can be broken down into kilograms times meters per second squared. The equation, we really only use one main equation, which is F equals ma, so the net force, and that could be in the x or y direction, has to equal the mass of the system times acceleration. One thing to note here is that if the system is multiple masses, you can add up the masses, and the net force on all the masses should equal the acceleration, and the acceleration should be the same for all the masses in the system. So let's say we had two boxes. If we made the system both boxes, we'd have to add the masses of the boxes, and both would have the same acceleration. We also have friction force, which is mu, this Greek m, and then normal force. The coefficient of friction could be about kinetic friction or static, which we'll get to later. And then typically the normal force is equal to the negative force of gravity, but not always. So actually, I should probably remove that from the formula chart. So let's look at our types of forces we have. So you have friction force, which is represented by capital F, lowercase f. You have gravity as a force, which is Fg. And applied force is kind of just generic. It could be someone pushing something or pulling something, but that's going to be Fa. Spring force is Fs. We don't really use electrical force or magnetic force, but if you did physics 2, physics 2 goes into electricity and magnetism. We also have normal force, which is represented by Fn, and then drag force is similar to friction, it's just with air. We typically don't have drag force in AP Physics 1. One thing I forgot to mention is there's also tension. When you think of tension, think ropes, and that would be represented by Ft or just capital T. So those are kind of our options for typical forces we have. If it's another specific force, it could probably be categorized as one of those forces anyways. Okay, so let's look at some definitions. A force that resists motion is called friction. The attractive force between objects with mass is called gravity. And one thing to note is that it does say attraction force between objects with mass. Actually anything with mass does have gravitational force. Like I have a gravitational force on this pin, and the pin also has a gravitational force on me. But if you think about the scale of the universe, the pin doesn't really pull me as much compared to what the Earth does, because it's not only about the masses of the two objects, but it's also about the distance between them, between the center of the objects. And so me and the pin, we don't really have very large masses or a large distance between us, but if you think about me versus the Earth, that gravity is going to matter. So we have to be aware of that. Also, it's good to know that force of gravity is the same as weight. Weight and mass are different. The mass is about your matter or atoms, and mass does not change going from one location to other. So if I was on the moon, I'd have the same mass as on Earth. But if we're thinking about weight, it really depends on the acceleration of gravity on that specific planet or wherever we're at. So force of gravity will be changing because your acceleration will change. It won't be negative 9.8, but the mass itself will not change. The force of an object from the surface it sits on is called the normal force. So the normal force is actually gets its name because it's perpendicular to the surface. So if we're talking in terms of math, a normal means that it's perpendicular or at a right angle. So the normal force, anytime you set an object down on a flat surface, that surface will be pushing back up against gravity. Or even if it's on an angled surface like a ramp, you still have a normal force. It'll just be skewed where it becomes perpendicular to the surface. And so it's not counteracting all of gravity. Okay, but normal force comes out of the surface that an object is sitting on, perpendicular to the surface. The last one, a pulling force along a rope, would be tension. The SI unit for force is the Newton, which if we look at the formula F equal ma, if force is newtons, you can look at the unit for mass and acceleration and notice that a newton should also be kilograms meters per second squared. So on the AP exam, sometimes they like to give newtons as the units broken down. So Newton's base units are actually kilograms meters per second squared. And that's also good for dimensional analysis. If you ever have to derive a different expression, it can help you to know what the base units are for newtons. A free body diagram, or shorthand, we have FBD, should show all of the forces acting on an object. And the object is represented just with a center of mass. So you just represent it as a dot or a square. You actually do not draw the full object usually. The vector sum of all forces, so the sum of all forces would be the net force, which is where we base our F equals ma. You have to have the net force. Okay, equilibrium, think of the word equal. If we're in equilibrium, the net force should be 0, resulting in no acceleration. Here's a common misconception though. When people hear no acceleration, they think the object has to be stopped. But that's not true. You could be moving, but you just may be moving with a constant velocity. So, like a car on cruise control, the car is not speeding up, it's not slowing down, and so it doesn't have an acceleration, it doesn't have any forces that are unbalanced, but it is still in motion. So that's a common misconception. And so that's where we get the two types of equilibrium to differentiate. We have static, which is no motion, and then dynamic is if you have a constant velocity. Oop. So if you have a constant velocity, there's still no acceleration. And if you don't have an acceleration, you don't have any forces pushing or pulling on that object. So it stays consistently. Maybe think about a box sliding on an ice rink. Box sliding on ice rink. I'm not pushing it. It's just sliding on its own, but there's no friction to stop it. And so it just stays moving with that consistent velocity. So that would be an example of dynamic equilibrium. Okay, so can something be in motion and still be in equilibrium? Yes, if speed is constant. Then no acceleration. Okay. Let's talk about free body diagrams. So one of the requirements for a free body diagram is you either draw it as a dot or a box. You have to draw the forces connecting to and from that box. And the arrows do have to touch the box or the circle. And the magnitude is going to matter. So let's just say I was pushing a box with 20 newtons to the right. And then there was a force of friction that was about, I don't know, 7 newtons. You would need to make sure that those arrow sizes are relative to the magnitude. So I made my 20 newton pushing force much greater than my 7 newton friction force. So you want to represent the size. You also want to make sure that the tail end of the arrow is always touching the dot. So, for example, this, hang on one second. If we were to draw the forces like that, this would not be acceptable because the arrowheads are touching the dot, and that's just a general formatting issue. They want to make sure that the tail ends are what's touching the dot or box, and so just think of it as the arrows sliding. You can slide the arrows around any way you want, just make sure you don't change like the angle that the arrows are at. So we keep it a flat horizontal line and just slide it to where the 20 newtons was on the right side and the 7 newtons was on the left. Also, if you have multiple forces, so let's say it was an elevator and the elevator had tension, and then we also had the force of gravity of the elevator, but we also had the force of gravity of a person. Okay, so if you have multiple forces, you actually do have to draw them side by side. That is a rule. And so what we would not want to see is Fg of the elevator on top of Fg of the person. This would be a no-go. The reason for that is when we're grading these, it's hard to tell if you intended for the magnitude of the person to be even larger than the magnitude of the elevator, and that wouldn't even make sense. The elevator should be heavier than the person. So with them stacked like that, it could be interpreted different ways. And so you always want to make sure that they are side by side, just like this example, the force of the person and the force of the elevator are separated and they're side by side. They're still both pointing down because they do need to be pointing down, but you cannot stack forces. Okay, so let's try these free body diagrams. A box sitting motionless on the floor. So you can draw a box or a dot, but we'd have the force of gravity. And then if it's sitting motionless, you should have a normal force pointing straight up and be equal in value. So these two forces are typically always there. Normal force is anytime it's sitting on something. So if a box is sitting motionless on the floor gives it that normal force. And then obviously we also have gravity because we do have a box that has some mass, so it should have some gravity. Okay, since we do want them to be equal in size because whatever gravity does downwards, the normal force should counteract it. Another way of thinking about it is our box isn't sinking through the floor and it's not floating into the air. So if it's not sinking or floating, they have to be in equilibrium. So they have to be in balance. We could also do a net force on this just to practice that. So for this example, you can either have a horizontal net force, F net X, or vertical F net Y, and you could do both, but they would have to be separate formulas. But for this one, we really only have F net in the Y direction. So the net force is equal to mass times acceleration, which would be equal to the normal force minus the force of gravity. Let me kind of explain that. So F net is always ma. But if we think about the actual forces, the normal force is acting upwards, and we associate up with positive, and then Fg is acting downwards. That would be the negative force. And so looking at the total forces, we should be taking the normal force and subtracting the force of gravity since that was in the negative. Since it is sitting motionless, we could also take this formula and simplify it. If there is no motion, then our F net should be 0. There is no acceleration. And so Fn minus Fg would stay there, but ma was shortened to 0. Okay, so there's an example of how to do a net force. Net force is always equal to ma, but then you could also set it equal to the forces being added together. Okay, a box with an applied force to the right. So let's just go ahead and draw our two forces that should always be there if we're on a surface and on Earth. You should have gravity and you should have normal force. And those are typical. Equal in value since it's not sinking, it's not floating, we need to be in balance. But we do have an applied force to the right. So I'm pushing it right. I want to make sure I draw it on the right side so the tail hits the box. So for this example, we could actually do an F net Y and an F net X. Okay, so an F net Y, they should, we're not sinking or floating, so they should be equal to 0. We have no acceleration in the Y direction. And it looks like the same scenario. Fn is my positive vector, so I'm going to add that. And I'm going to subtract Fg because that one is pointing downwards. So that would be my negative vector. For F net x, since I only have an applied force to the right, I really should have an acceleration. So I'm going to put ma. It is accelerating. There's only one force, and that one's to the right. There is no force to the left. So there has to be some sort of acceleration. But there's only one force, so it should just equal Fa. Whatever Fa is, that's going to control the acceleration. Okay, a box with an applied force to the right, accelerating right with friction. So let's do Fn, Fg. We have a applied force to the right again, but we do have friction, and I need to think about that because friction could be the same size as the applied force, or it could be less than the applied force. So looking at the wording, it says it is accelerating right. And so that hint is telling you the total net force should be to the right. If it's accelerating right, the net force should be to the right. And so what that's telling me is my Fa should be bigger than my Ff, my force of friction. That way there is a net force heading to the right. It doesn't all cancel out. Okay, we can do two F net equations. We can do F net y, F net x. F net y, in the y direction, we should have no acceleration, and it's Fn minus Fg again. For F net x, it is telling us that we're accelerating, and remember, right is positive, left is negative. So if I wanted to sum up my forces, I do Fa minus Ff. Remember, acceleration, we should get a positive answer for that since it is accelerating right, so I'm just making that note. My A should be positive. Okay, a box with an applied force to the right, accelerating left with friction. Actually, that doesn't even make sense because friction would have to be bigger, and friction cannot be bigger than the force you're applying. Think of friction as like a reactive force. Whatever you push, friction's going to push back. But friction can't push more than that ever. It's a reactive force. So I really shouldn't have put that. But let's say an applied force to the right and constant velocity. Let's do that instead. So what do we know about constant velocity? If it's constant velocity, the overall acceleration should be 0. And so if I apply a force to the right, I need an acceleration of 0, which means that the net force should be 0. So if I apply the force to the right, there should be an equal force acting left. Let's see. So let me do my typical y. We're not sinking or floating, so the y should be 0, and then it would be Fn minus Fg. For F net x, this time we have constant velocity, acceleration of 0. And so our net force should be 0. Just based off the wording, we knew how to make the magnitudes of the arrows appear. We needed them equal so they cancel out, so we didn't accelerate. Remember, right is positive, so I'm going to do Fa minus Ff. Okay, this one we're not going to go into detail quite yet. There's a whole separate lesson, but a box sliding down a ramp with friction. In fact, let me zoom in even more. Okay, so when you have a box on a ramp, everything is kind of tilted on its side. And what we do is we actually tilt our y and x axis. So we consider x being along the surface of the ramp and y being perpendicular to the surface of the ramp. So if you tilt your head, it looks like a normal y and x. So everything is kind of just skewed on its side. Let's look at this box. So on the box, you just have to think about the force of gravity. The force of gravity comes from the Earth. And the force of gravity pulls you towards the Earth's surface. And so even though we're at an angle on the ramp, the force of gravity should not be at an angle. The force of gravity is going to point straight down towards the Earth's surface. Now, the second thing I have to think about is how would the surface of the ramp push? How would the normal force be? Usually, normal force counteracts all of gravity, but now gravity is pointing straight down and my box is at an angle. What you have to remember is that the normal force has to be perpendicular to the surface. Okay, so if you tilt your head, the normal force should be coming straight out of the ramp. And actually, another thing to note is that the normal force does not have to counteract all of gravity. So it actually should be a little bit shorter than Fg this time. And let me just restate what I said. So since force of gravity is not directly across from Fn, Fn doesn't have to counteract all of gravity. It only has to counteract a portion of it. And so that's why you have like a smaller Fg. It says the box is sliding down the ramp, but with friction. So if we're sliding down, friction should be pointing up. Okay, and that would be the free body diagram for a ramp. Later on, I'm going to teach you how to break down force of gravity into the y and x components. But for right now, this would be how they want you to draw the free body diagram on the AP exam. They actually don't want you to break down F of G in a free body diagram. So we'll just look at that later. All right, a pulley system where they are in equilibrium. So your net force should be 0. Okay, so usually a pulley system consists of 2 masses at least. It could be more than that. If there's no net force, then it is not accelerating. So you wouldn't be rotating either way. None of the masses should be falling. Okay, so here's what you have to do for a pulley. Since it's 2 masses, you actually have to do 2 separate free body diagrams on that. Okay, so obviously we'd have Fg for both masses. So I'm going to also label them as Fg mass 1 and Fg mass 2, just to differentiate. And then we also have a rope, and with ropes, there's tension. Something to know about ropes is if they are ideal ropes, which most of ours are going to be ideal unless it explicitly states it's not an ideal rope. But if our ropes are going to be ideal, meaning they don't stretch or compress, and they also don't have mass to consider. So the rope itself is supposed to be massless. And if our strings are ideal, if it's the same section of rope, then it should be the same tension. And so with pulleys, you have the rope tied to mass 1, it's wound around the pulley and then it's tied to mass 2, but it's still the same section of rope. It hasn't been cut and it's a continuous rope. So the tension on mass 1 should be equal to the tension on mass 2. So we don't need to label them as T1 and T2. It is just tension. They are the same. Okay, and then you would have to do 2 separate F net equations. So for F net 1, if it's in equilibrium, it should add up to 0. And then you have tension minus Fg1. And then for F net 2, it also equals 0, and we have tension minus Fg2. Okay, so that's how you deal with pulleys. You have 2 separate masses, you do 2 separate free body diagrams, and then you do 2 separate F net equations. And just remember that the tension in the rope is equal on both sides. All right, a person standing on an elevator with an acceleration up. Okay, so let's pay attention to this wording, a person. So it doesn't want the free body diagram of the elevator. It wants the free body diagram of the person. If it did ask for the elevator, for elevator, it's usually pulled up by cables, and so we'd have some sort of tension. But since it asked for the person's not being pulled by a cable, so we should see no tension. Instead, what the person is experiencing, they're being pushed by the floor of the elevator. They're either being pushed up or pushed down. The person is experiencing only forces from the ground of the elevator, which should be a normal force. So just be careful that it is not experiencing tension. The person is experiencing a normal force. Okay, so we are accelerating up, which is in general positive. And so if we are accelerating up, you should have a positive net force. Another way of thinking about it is if we are accelerating upwards, the upward force should be larger than the downward force. Okay, so obviously we have the force of gravity of the person. Um, since it is a person, we don't have to consider the force of gravity of the elevator. We're talking about like me standing on the elevator. So it'd just be my gravity. And then the normal force, since we're accelerating up, I want to make that bigger than the gravity pulling down. So this time we do have an F net Y. I'm just going to put MA. I don't know what the mass of the person is or the acceleration, but that's the setup for it. And then normal force is positive, force of gravity is negative. And we should be getting a positive answer for acceleration since it said it was accelerating up. Okay, a pulley system with an angular acceleration counterclockwise. So almost the same pulley system as before, but this time we're accelerating counterclockwise, which don't ask me why, but when you accelerate counterclockwise, it is a positive acceleration. So that's just one thing to note. It's kind of counterintuitive because usually you think clockwise would be positive, but in physics, counterclockwise is positive. And that's actually going to help us make our net force equations. Once you know the way it's accelerating, you kind of want to make yourself a note. This is the positive direction going down. Since the whole system is accelerating counterclockwise, for mass 1 going down, we're going to make that the positive direction. And for mass 2 going up is going to be the positive direction. We're going to have to make some sort of sense of it. And remember, in physics, you can choose your positive and negative. So we always choose up as positive and right as positive. But you could make down positive if you wanted to. With pulley systems, since it's kind of an angular acceleration, both objects are moving together, you need to come up with a system of what you want to be positive and negative based on the direction it's accelerating. So since mass 1 is accelerating down, let's make down be positive. Since mass 2 is going to be accelerating up, let's make up positive. Okay, so that's something to know about pulleys. We'll practice that more. This isn't the only time I'm going to say that. So if you don't get that now, that's okay. So since the mass 1 is accelerating down, we have FG1. The tension should not be as great as FG1. That way we have an overall, we're accelerating down, and so we need a bigger force on the bottom. For mass 2, it's accelerating up. So we have tension, and I want to make them kind of the same size because they are the same section of rope. And then for the force going down, we have FG2. And it's accelerating up, so that tension should be bigger than the FG2. Let's do F net of mass 1. So for mass 1, we have mass times acceleration. And let's look at our acceleration. So we're accelerating down. We want to make down positive, and that's going to be weird at first. But since it's falling down, down is positive. So FG1 is going to be positive, and subtract tension from that. Tension is pulling against the motion. So that's another way of thinking about it. FG1 is working with the motion, tension is pulling against the motion. So we need to make that distinction. I'm also going to write mass 1, acceleration 1, because we're talking about only mass 1. We're not talking about mass 2 for this. It's a 2-object system, so we really need to make sure we distinguish that. We're also going to put mass 2, A2, and then it should be this time, if we look at our acceleration, it's accelerating up, so up should be positive, so tension is going to be positive, and FG2 is acting against that tension. Okay, so there's your net forces. We have object 1, object 2. For acceleration, since it's the same rope, the same pulley, they should actually accelerate the same, but the masses for those equations are going to be different. Okay, so that is a free body diagrams. Now let's talk about Newton's 3 laws of motion. The first law is that an object in motion will stay in motion and an object at rest will stay at rest. And this idea is called inertia. So another way of thinking of inertia is resistance to changing its state of motion. So if it's let's say an elephant is running. Elephants have a very large mass and they tend to resist changes in motion. So if an elephant's running, it's going to take a lot of force to stop it from running, and it's going to take a long time for it to slow down. So it really depends on the mass of the object, how much inertia it's going to have. The first law is also referred to as the law of inertia. So if you ever hear that, law of inertia is Newton's first law. And you will have to know which law is which for the AP exam, because sometimes it'll just say justify using Newton's first law or Newton's second law, and you're going to have to know which one's which. Newton's second law is known as the formula law. It states that an object under the effect of a net external force will accelerate in the direction of the net external force. So let's talk about what external means. External is a force acting outside of the system. And you can define your own system. So let's take a simple example. We have the girl sitting in a wagon and the man is pushing the wagon. Now, in this system, or I guess I should say in this picture, we have three objects. We have the girl, wagon, and man. But there's a logical system that you can define. So let me just give you all the options. You could circle just the girl and do a free body diagram of the girl. You could circle the girl and the wagon and do a free body diagram of the girl and the wagon together. Or we could circle all three objects and do the girl, the wagon, and the man. But for this example, the easiest thing to do is to take the girl and the wagon as a system. Because they are touching each other, they're going to experience the same force and they're going to be accelerating together. So it just makes sense that that's the system. The man is the external force. And if you have an external force, you will have a change in motion. Change in specifically velocity, because you're going to have an acceleration. Okay, so that's what we mean by external force. You define your system, and anything outside of that is external. Newton's second law can be stated like this: a net external force acting on a mass causes a mass to accelerate. The acceleration is, I should have said directly proportional to the force and inversely proportional to the mass. And that can be seen with the formula. So let's say we kept the mass the same. If you look at force, if we increase the force, what should happen to our acceleration? And you can think about this conceptually, or you can think about the formula. So let's just take a box. So we have a set box. If I push it lightly, we should have a very low acceleration. But if I took that same box with the same mass and I pushed it with a very large force, we should have a large acceleration. So it looks like whatever happens to the force, the same thing will happen to the acceleration, which makes it direct. If you can't think about it conceptually, if we rearrange this formula, it's F divided by A equals M. So if you keep mass the same, force and acceleration are being divided, and anything that is division is going to be a direct relationship, because if one goes up, the other has to go up to maintain like the same value. Let's look at if we kept the force the same. So if we keep the force the same, mass is being multiplied by acceleration. So just looking at the formula, anytime you have multiplication, that's going to be an inverse relationship. So if mass goes up, acceleration goes down, and vice versa. So there's where the formula for direct, it's division. For multiplication, it's inverse. But if you want to think about it conceptually, a good example would be moving an elephant versus a feather. If I keep my force the same, so I push the elephant with the same force I push the feather, the elephant will barely accelerate because an elephant is way larger than I am. But if I push a feather, it would cause a large acceleration. So if you keep your force the same, big mass, little acceleration, and then little mass, big acceleration, causing an inverse relationship. The last law is, I think, the most common one I've seen on the AP exam as far as like justifying or even the multiple choice that are tricky. A lot of them, the key is knowing Newton's third law. It's called the law of action reaction. So for every force, there is an equal but opposite um, reaction force. Okay, so here's some rules. They have to act on different objects, so they can't be in the same free body diagram. That means Fn and Fg break this rule. So they are not action reaction pair. And I can't state that enough. That's the most common misconception, is that normal force and gravity are an action and a reaction. Gravity is the action, normal force is the reaction, and that's just not true at all. They have to be acting on different objects, and I'll show you what the pairs look like on that. They have to be equal in magnitude because they're equal. They have to be opposite, so if one goes up, the other goes down, and one cannot exist without the other. So here is the action reaction for force of gravity. The action the action would be the earth pulling on the ball. The reaction would be that ball pulling back on the earth. Because the ball does pull on the earth, everything has a gravitational force. It's just the way it's perceived. So the earth pulling on the earth has an insane mass, and the ball has a tiny mass. And so then we get a large acceleration that we can visibly see. But with the reaction, the ball pulling back on the earth, the ball has such a small mass compared to the earth that it hardly experiences any, or actually really no, change in acceleration. But that's the action reaction pair. And then for the normal force, so let's just take a book sitting on a table. The book pushes down on the table, and then in turn, the table pushes on the book. And so there's your action reaction. The book's pushing down, the table's pushing back up. But Fn and Fg are not action reaction pairs because Fn and Fg are on the same free body diagram, on the same object, and action reaction is an interaction between two things. Okay, so let's just look at these quick examples. A bullet is loaded in a rifle and the trigger is pulled. The force experienced by the bullet, okay, so this is the third law. Every force has an equal but opposite force. So the force of the bullet should be the same as the rifle. And that's due to the third law. That's an action and a reaction to that action. Okay, so if we're talking about acceleration, let's look at the formula so we can see how everything relates. I'm keeping the force the same because the rifle and the bullet experience the same force, and we just proved that with Newton's third law. But it says the resulting acceleration of the bullet. So let's think about the bullet. For the bullet, the mass is smaller, and so what would we experience with our acceleration? Well, with smaller masses, they experience a larger acceleration if it's the same force, so greater than the rifle. And that's proved with the second law. Okay, so if we need to know how different variables are related, that's the second law. But if it talks about what force does one object experience versus another object, that's Newton's third law. Okay, so let's do some more. A Mack truck and a Volkswagen have a head-on collision. Which vehicle experienced the greatest force? So anytime you see that keyword force, they should both be the same, and that's third law. Every force has an equal but opposite reaction force. If we're talking about acceleration, the Volkswagen has a larger acceleration because its mass is smaller. Kind of going back to the bullet versus rifle. Okay, the apple is at rest on the table. If we call the gravitational force exerted on the apple an action, what is the reaction? So we're talking about gravitational force exerted on the apple. So don't focus on the table. For the apple, the earth pulls the apple. The reaction to that has nothing to do with the table. The reaction to that would be the apple pulling back on the earth. And notice that the action reaction pair deals with the same objects. So if the earth is pulling on the apple has to pull back on the earth. The table was never mentioned, and the table is not part of that pair. So that's a good way to know. You should be talking about the same objects. Here's some action reaction. Friction on the road. So the tire pushes on the road pushes back on the tire, and that's how we accelerate. Rocket fuel, the fuel ejects outwards, and when it ejects out, the rocket goes to the right. And we already talked about gravity. All right, here's a second law example. So we have a 400 kilogram hippopotamus. And it should experience a normal force. It is pushed with a 200 Newton force by the guy. So I'm going to put it going to the right. The rusty cartwheels produce a 50 Newton friction force. So that's in the opposite direction. I know my F net Y should be 0, but I do have an F net X. Okay, so I know my F net Y should be 0, but I do have an F net X, which I don't know the acceleration yet. But I have another option. Instead of doing mass times acceleration, I could just take 200, subtract 50. Remember, 200 is a positive force, so I'm going to make that positive 200. And then 50, since it's heading to the left, would be negative. So that's why I did 200 minus 50, and then I got 150 newtons. Okay. Oh, here's part B says, what is the acceleration? Okay, well, F net does equal ma, and we did figure out that the net force is 150 newtons. Okay, well, I do also have the mass. I have 400 kilograms. I still don't know A, and then 150. So just replacing everything I know. Solve for A, so if we're multiplying by 400, divide by 400. So 150 divided by 400 would give me 0.375, and remember, acceleration is meters per second squared. Okay, so here's a ranking problem. We have A, B, C, D. It says rank the following situations based on magnitude of the net force. So no positive or negative if it's magnitude. And it says at the bottom of block 2. So we really want to do a free body diagram on just object 2. Now you could go through it and do the free body diagram. So like in A, you would have the force of gravity of 200, but also this force of gravity of 100. Both of them should be acting down. And it experiences both gravities since they're stacked on top of each other. But I know since there's no acceleration, these are motionless, then the net force should be 0. And if the net force should be 0, whatever gravity it's experiencing down, the net force should counteract everything. And so we'll see a giant Fn, a giant normal force, to counteract both gravities. But once you realize that acceleration is 0 and net force is 0, this makes this problem really easy because it asks rank the net force. Well, all of these are motionless, so I don't even need to do any work. I just need to know, if it's motionless, all the forces should cancel. So A is going to be equal to B, is going to be equal to C, is going to be equal to D, because they are all not accelerating, which means our net force should be 0. I mean, it could be I don't even know how they would ask a question. It could ask, what's the total forces of gravity experience on object 2? But this is all we needed to know. If there's no acceleration, the net force is 0. Okay. Many automobiles suffer neck injuries when struck by cars from behind. How does Newton's first law, the law of inertia, apply? That one's easy. An object in motion will stay in motion unless acted upon by an outside force. And so your body, it was accelerating when the car is going 70 miles per hour, let's say. So when you get in an accident, the car may stop, but you have a tendency to keep moving forward until you experience the force a little bit later. So you're going to continue to move forward. Um, but that changing acceleration, you're going to go from going 75 miles forward to going backwards. And that intense change in acceleration does cause whiplash a lot of times. So it says, um, how would a headrest help against this type of injury? The headrest will just prevent that full change in acceleration from happening. And so you don't experience all the change in motion, and it helps lower the injuries. So just to counteract some of the force. An old trick consists of quickly pulling a tablecloth underneath items on a table, leaving the table is undisturbed. Which of Newton's laws, first or second, explains this trick? First, because an object in motion stays in motion, but also an object at rest will stay at rest. Just a tendency, though. It's not always going to stay at rest. That's why you have to pull it quickly, or it's not going to work. Because if you don't pull it quickly, it's going to experience more of the force, and it does cause a change in motion. Newton's first or second law, if an elephant were chasing you, its enormous mass would be very threatening, but if you zigzag, the elephant mass would be to your advantage. This is about inertia. Large mass will resist change. So if you're zigzagging, the elephant's going to have a harder time zigzagging because the larger masses can't change motion as easily as a smaller mass. Okay, so that's it for this video. We talked about how to draw free body diagrams, make sure that you only use a dot or a box, and make sure that your tail ends connect to the box, not the head of the arrow. And then also always think about magnitude. You want to make the vector's relative magnitude apparent. So if a force is really large, make the vector larger, and if it's smaller, make it smaller. Which kind of seems like common sense, but a lot of students forget to do that. And then we also talked about the 3 laws of motion. Remember, the first law is the law of inertia. An object in motion stays in motion. An object at rest will stay at rest. The second law deals with the formula, so F equals ma. So it can help you think about whether they're inversely or directly related. Remember, if they're being multiplied, that's an inverse relationship. And if they're being divided, that's a direct relationship. And then the third law is every action has an equal but opposite reaction force. So it's talking about specifically the forces. And remember that the normal force and force of gravity do not count as action-reaction pairs. Okay, so that's it for this video. We'll pick up on the normal force and friction force when we come back.